Hey, it's Ben, and welcome to Lecture 7 of Open Project Space. This time we are talking about timers and interrupts. Hopefully some of these topics might help clarify concepts learned earlier in the program, like pulse width modulation or PWM, for example. And then it'll also help you take code that you have written for past projects and make it more clean, more efficient. For example, you've created a project before that involved buttons. You'll learn how to improve the code you wrote for handling those button press events after this lecture. So hopefully, our discussion today on timers and interrupts will be a form of enlightenment as you reflect on your past projects and consider some of your future ones. So let's talk about timers. Right, think back to our discussion of microcontroller architecture. We had the CPU, we had a memory module, I/O ports, USART, SPI. We covered those in our communication protocols lecture. We also talked about ADC, the analog to digital converter used by functions like analog read in the Arduino Nano. This time, we're going to talk about the timer module. Remember that timers are used by the microcontroller to control the timing of program execution or output signals, and also to measure time. So let's talk about some types of timers we might encounter. These timer types can be distinguished by when the timeout triggers. Well, what is a timeout? A timeout is an event that occurs after a preset period of time. So we have a one-shot timer that has a single timeout. In a single timeout, for the timer to be run again, it must be reloaded manually. So an example of a one-shot timer would be a countdown timer. Let's say we have a 10-second countdown. As time elapses, we go from 10 to 9, 8, 7, all the way to 0, where the countdown timer stops. And for us to start that timer again, we must reload it manually, bring it back to 10, and then we can start the countdown over. That's a one-shot timer. We also have a periodic timer, or auto reload timer. We can infer from this that a periodic timer would have periodic timeouts that occur at a fixed interval. So this timer would reload automatically. This is like, for an example, an alarm clock in your bedroom. That alarm clock is set to ring once every morning, maybe at like 8 a.m. You don't have to manually reload it each time it rings. It's automatically reset, and the next day it rings at the same time. That's a periodic timeout. So let's consider some of the use cases for these timers we might encounter. One common use case in our world of embedded systems would be to pause or delay the program. For example, when you use Arduino, you might call the delay function. This uses a timer to suspend code execution for a specific period of time. I bet you could figure out what type of timer this is. Going back to the previous slide, it's probably a one-shot timer. This is also considered a blocking timer function since it blocks program execution. When delay is called, everything freezes. We wait for a specific amount of time, and then the program continues. We might use timers for measuring time. For example, the millis function in Arduino uses a timer to count the number of milliseconds that have elapsed since the program began. This is a non-blocking timer function, since the program continues to execute as the timer runs. So we can call milliseconds. It doesn't have to pause the program. It just goes to a timer module within the Arduino Nano. It performs some operation to convert the value of that timer into the number of milliseconds that have elapsed since the program started, and then it returns that value. Here are two other use cases. We might call a function upon timeout. So when that timer suspends, as a programmer, we would probably want a specific function to occur, in which case we would call a function to handle the event. We're going to actually come back to this in a couple of slides. And that last case should look somewhat familiar. We would use timers to generate a PWM signal. When you call analog write from your Arduino, that uses a timer to generate the PWM signal and more importantly, to time the rising and falling edges of the PWM waveform. So the frequency of that PWM signal is aided, or it's generated by a timer within the Arduino. And if you just need a refresher on how analog write works or what exactly PWM is, I invite you to go back to the microcontroller architecture and Arduino lecture. So let's talk about the timers within the Arduino Nano specifically. The Arduino Nano has 3 general purpose timers, or GPTs. These timers are, remember, hardware, physical hardware, or modules within the microcontroller. And they're used for various functions, like we talked about in the previous slides. They might be used for PWM. You might use a timer for delays. You might use a timer for measuring time. Conveniently, the digital pins of the Arduino Nano are capable of carrying the output of a timer, or the timer rather, to which they are connected. So let's discuss that just a little further. We have those 3 Arduino Nano timers in the diagram here. Each of them is actually connected to 2 digital pins. So for timer 0, that's D5 and D6. Timer 1 is D9 and D10, and for timer 2, that's D3 and D11. And so when we configure our program and we say want to generate a PWM signal to pin D5, what we're doing when we call that function analog write is we're telling the Arduino Nano, hey, I'm using pin D5. I want it to connect with timer 0, and I want timer 0 to output a PWM waveform to D5. But it's also important to remember, if you are using pin D5, for example, to output a PWM signal, you can't also use that pin for a different purpose. You couldn't output a PWM signal from pin D5 at the same time you were using digital write or digital read. A pin can only be configured to one function at a time typically. And it's also important to remember that not all of these timers have the same specifications. And so timer 0 and timer 2 actually only store 8 bits worth of data, whereas timer 1 stores twice the number of bits, up to 16 bits. And so their use cases through the Arduino built-in library and some of the other libraries out there change. For example, timer 0 is actually used by the delay and millis functions of the Arduino built-in library. And so if you use delay or millis, that's a function call that always makes use of timer 0. Whereas if you call the function tone, that's going to be used by timer 2 specifically. And then there's the Arduino servo library. A servo or servo motor is a component whose angular position you can control through a PWM signal. And so when you send different PWM signals, that changes the position of the servo motor. So if we rely on PWM to set the angular position, then naturally we want a higher resolution signal sent, a signal which can be more precise. And to summarize our discussion on Arduino Nano timers, we have to keep in mind that we really only have 3 timers here. And so we have to use them wisely, because if you, in your program, wanted to use the same timer at the same time for 2 different purposes, you'd get into trouble. For example, if you wanted to output unique PWM signals to both pins D5 and D6, you'd be in trouble because internally they're both connected to timer 0. Timer 0 can't feasibly output 2 unique PWM waveforms at the same time. And keep in mind, your compiler likely won't catch this issue either. And so if you do misuse these timers, you won't necessarily get some explicit error. You'll just see unexpected behavior. And what I mean by unexpected behavior is really, if you're using an RGB LED, the light might flicker. If you are using a servo motor, the angular position might not be what you expected. That kind of unexpected behavior. So we talked about general purpose timers. The Arduino Nano has 3 of them. But it's also equipped with a WDT, or watchdog timer. And this has a special use case. It is used to detect and recover from software or hardware errors. How does it do this? Well, the WDT is basically a countdown timer, and it'll count down to 0. And each time the program's main loop is run, the timer will be reset. So what happens if the WDT, the watchdog timer, counts down to 0 before the main loop finishes running? Well, then the WDT will reset the entire processor. So the idea here is that if the main loop runs for too long, then an error probably occurred. And so the WDT will reset the processor. But this is not a perfect solution, because sometimes a program loop just takes a long time because the code takes a long time to run. And so the WDT is a very imprecise method of detecting and recovering from errors, because it'll just incorrectly assume a fault exists if the program takes too long, and then it'll just constantly reset the program. But it exists as an option, and it does work for some simple use cases in embedded systems. Let's talk about how you can use an Arduino timer to measure time. So we're going to use one of the Arduino's internal timers, and it'll be done through this simple timer library, which is basically an abstraction of the built-in function millis that is used to count the number of milliseconds since the program started. But we're going to keep it simple here. Let's say you wanted to use timers to call other functions. Then you could check the timer interrupt library, but we're not going to discuss it here in this lecture. So this library is pretty simple to use. We're going to instantiate a timer as such, and then we are going to call its member functions. Time is going to be measured in milliseconds by default. Keep that in mind. But when you instantiate this object, if you were to include the parentheses and pass micros as an argument to that constructor, you could instead measure in microseconds. But again, back to the member functions. So we've got this timer object. If we want to start the timer, we call timer.start. This will put the timer in the running state. Now time is being measured, elapsed time. We can pause it. This will put the timer in the pause state, and the time elapsed will freeze. When we're ready to resume it, we call timer.resume, and it'll resume and put the timer back in the running state. Lastly, as far as pausing, starting, and stopping the timer goes, we have the timer.stop function, which of course stops the timer. When we've reached the stop state, this is like our reset position, the time elapsed is going to stop now. And the next time you call timer.start, it will reset the time elapsed. You can't call timer.pause or resume anymore. You can only call start after this. But before you do so, you probably want to read the time elapsed. And so you'll call timer.read. And that again will return the time elapsed overall in milliseconds. And if you wanted to check the state of the timer as you're using the other functions, you can call timer.state. It'll return one of 3 constants: running, paused, or stopped. And that's it. Super simple. Let's talk about that second big concept of this lecture: interrupts. What is an interrupt? It is a request for the CPU to halt the currently executing code when an event occurs. The CPU will literally suspend the current program. It's going to halt the currently executing code in order to handle this event. And it's going to do so by calling or executing another function called the interrupt handler. See, quite convenient. To handle the event, we're going to call the interrupt handler. It's also known as the interrupt service routine, or ISR. When this interrupt handler finishes execution, the CPU is then going to return to the old program and continue execution. We have two different types of interrupts. One is a software interrupt. It's triggered by an instruction. Software interrupts are also called traps or exceptions. They're often caused by an illegal operation. For example, you divided by 0. Bam, that's an exception. For example, you access memory without permission. This is known as a segmentation fault, and this is another exception. On the other end of things, we have hardware interrupts. These are triggered by devices external to the CPU. So think as literally as you can about this statement, devices external to the CPU. We're not talking about external to the Arduino Nano necessarily. Other devices or hardware within the microcontroller can trigger hardware interrupts. For example, a timer. So hardware interrupts are also known as external interrupts. They're caused when a device sends an interrupt request or IRQ signal to the CPU. Again, timers can trigger external interrupts. So when the timer times out, it might send an interrupt request or IRQ signal to the CPU. The same might occur when, say, a user presses a button, or when the power supply fails on the microcontroller. That might send an IRQ to the CPU. Lots of different use cases. So let's talk about an alternative to interrupts that you have undoubtedly used in your projects up until this point. Polling. Polling is a method of periodically checking the status of a device. For example, you might check your phone for new messages every 10 minutes. That's polling. You're periodically checking your phone for messages. And so inherent to that process, it's going to cost you additional time. And the danger is, in this example, as a person checking your phone, if there are no new messages, that's wasted time. So interrupts are supposed to be our alternative. Interrupts signal when an event occurs, whereas polling checks to see if an event has occurred. And so an example of an interrupt would be, instead of checking your phone every so often, you're just going to read your phone when you receive a push notification. The push notification is the interrupt. And so there's a potential here by interrupts to save CPU time compared to polling. And so the simple rule I suggest you stick by is to use interrupts when an event is urgent or infrequent. And the reasoning behind this is, if an event is urgent, then you want an interrupt to signal that immediately. You don't want to wait until the next poll or the next time you check the status of a device, because then the event may have occurred seconds before. You also want to use interrupts when the event is infrequent. And the reasoning behind this is, if you poll very frequently for an event that occurs very frequently, then each poll should be a hit and you're not wasting a lot of CPU time. If it's less frequent, then interrupts, which only trigger when the event occurs, are the better option. Now, I mentioned earlier that you've used polling before, and I'll give you an example of this. When you wrote your code for a project involving push-button switches with the Arduino, you likely did so in the main loop. And what you did was, every time the loop iterates, you read the state of the push button and you check to see if it's a high or low voltage. And if it's a high voltage, maybe then an event has occurred and you trigger some other code. But effectively, through this main loop, you are polling, and you are probably checking more times than an event hasn't occurred for the event. So it's wasted CPU time. So instead, we could use interrupts for push-button switches. So here are our two common interrupt use cases. It'll be servicing timers Again, so when a timeout occurs, the programmer may want specific code to run. When the timer does this, it'll send an IRQ, and then the interrupt handler is called. And our other situation would be handling peripheral device events. When a key is pressed, for example, on a keyboard, that might send an IRQ to the computer, depending on the type of keyboard, and then an interrupt handler responds to the event. Again, you might use a push button in an Arduino project. That's a peripheral device event that could be handled through the use of interrupts. Now, how do we set up interrupts with Arduino? It's pretty simple. You have one built-in function called attach interrupt. Now, keep in mind, this can only be used for two digital pins, D2 and D3. These are the only two pins that can be configured for external interrupts. Attach interrupt is the function which we will call to initialize the external interrupts. And this function, as you can see in the declaration, has just 3 parameters. Let's talk about them. The first one is interrupt. This is the interrupt number, not a pin number. This is the interrupt number that you want to initialize. And only one interrupt can be initialized per interrupt number. The next parameter, ISR, is the name of the function you want to call as an interrupt handler. Remember, ISR stands for interrupt service routine. That is a synonym for interrupt handler. So for this function, this interrupt handler, you are responsible for defining it. And you're going to pass its name as this second parameter. Our last parameter, mode, is what configures the timing of the IRQ, or the interrupt request. You get to set this, so let's talk about the options. You could set the mode to low. And so for the digital pin to which you've configured this interrupt, when the pin voltage is low, that is what triggers the IRQ. You could set it to change instead. This triggers the IRQ whenever the pin changes value from low to high, high to low, whatever. Whenever it changes. You could set it to falling mode. It only triggers the IRQ when the pin voltage changes from high to low. So if we looked at this waveform over here, it would only be triggered when we go on the falling edge of a digital signal. The alternative would be rising, of course. So when the pin voltage changes from low to high, this is when we're on the rising edge of a digital signal. That's when the IRQ will trigger for that last mode. So again, 4 options, 4 modes. You are going to pass arguments to all 3 of these parameters. Call this function in the setup function of the Arduino program. One more thing though. We need to figure out that interrupt number because you have the digital pin number and you need to convert it now to an interrupt number. And you do so with this function, digital pin to interrupt. It has just one parameter, and that's the digital pin number. So you'll call it, you'll pass the digital pin number, and then it'll return the interrupt number that you'll use for the first parameter of attach interrupt. And it's actually recommended that you do it all in one line. So when you call attach interrupt, you're going to do it with digital pin to interrupt called in the first argument. And then you include ISR and mode. And this helps avoid the confusion involving digital pin and interrupt numbers and the difference between them. And that's it. I know this was a short lecture compared to some of our previous topics, but that's just because you've learned so much up until this point. And I promise you there's still so much more to come. We're going to talk about PCB design. We're going to talk about creating your new projects and how you should manage them using professional tools like version control. But for now, I bid you adieu, and I wish you a wonderful morning, afternoon, or evening, wherever you are, whoever you are. Thank you, and stay awesome.